excuse me. What I'm going to do today is get into where we left off on when did we leave off? Tuesday, I guess. I want to cover the whole idea of I want to talk about the periodic table and how the electrons are organized. Monday, I want to talk about further details on orbitals. Wednesday, I want to talk about ions and electronic configuration of those ions. So today, I mean, it's going to get further and further details. Now, the periodic table is very conveniently organized. Have we started to record? I just wanted to make sure we were recording. It doesn't say on the screen whether we're recording or not. Okay, anyway. Okay, so the periodic table is actually set up very conveniently to kind of describe all of the types of electrons, how they're configured, and what orbitals they're in. Now, remember we talked about on Tuesday, orbitals are areas of electrons where they can become very stable. They're, when they reside in orbitals, they're very stable. When they were outside the orbitals, they're very unstable. So they, to minimize energy, remember we talk energy, when we talk in this class of energy, excuse me, we are talking about two things. We're talking about potential energy and randomness. We haven't talked very much at all about randomness, for real, but for right now, we're talking about, let's just think about potential energy. So we want a potential energy is always more stable than high potential energy. So these areas of orbitals, the electrons want to be there because they're more stable. Remember, stability rules the game in the universe. Things want to become more stable, not less stable. So when we have electrons around the nucleus, they want to be in the most stable place they can be. Okay. So we've got this periodic table here, and we've got these areas designated as S's, P's, D's, and F. And those are orbitals that are, again, really stable. And it depends on how many electrons are in the element, how these electrons will then disperse themselves throughout these areas, S, P, D, and F. The more electrons, the more complex it gets, just because they're all kind of scattered all over the place. But if you have a few electrons, it's very, very straightforward. So last time we went over some really simple elements like hydrogen, helium, lithium. I want to continue doing that. Now, what I'm going to do also is show you a method one of my students invented a long time ago. Probably 11 years ago, one of my students in my pre-nursing class invented this method, and it really works well. And I've been using it ever since. I'm gonna give her name is Chris, very, very intelligent young woman. She was a single woman, a single mother, 3 kids, worked full-time, and got an A in my classes. just a brilliant woman, extremely hard worker, and just wanted to raise herself and become successful in something she wanted to do. And she did it. Not only she did it extremely well. Okay, so let's look at, and I'm going to put a periodic table right over here. And so we can refer to it. And the periodic table I'm going to be using is one that is not this one. I want one with is less complicated. Okay, so we're going to do insert a printout, and it's going to be and it always sticks it at the end, so we need to move it. Okay, so here's a periodic table, and it does not have any of the configurations on it like this. And what I want to do is show you how those were derived. Okay, so as a review from last week, let's choose something like helium. Now, helium has 2 electrons, and we want to know what those electrons look like in terms of the configuration. And what I mean by configuration is, where are those orbitals? Now, on Monday, I'm going to talk about, when I say orbitals, there are shapes to these orbitals as well. The S has a certain shape, the P's have a certain shape, the D's have a certain shape, and the F's have a certain shape. The F's are the most complex, the S are the simplest. Okay, so if we look at 2 electrons, remember there are core electrons and valence electrons. Core electrons are the innermost electrons. They are extremely stable. And the valence electrons are not stable. So what valence electrons want to do is become more stable by either combining or shedding electrons, gaining electrons, or whatever. So the idea is to become stable. Again, I keep emphasizing this in this course. I'm going to continue the whole semester. Stability is the name of the game. We want to become more stable. So if we're not stable, we want to become more stable by doing something, okay? All right, so we have a helium here. Helium has 2 electrons, okay? And we'll notice helium here has S block electrons, and there are 2 of them, okay? So we designate that as okay, shell and a period are the same thing. And the S is a subshell of the shell. A subshell is beneath the shell. So a shell is composed of its subshells. At the simplest level of shell 1, we only have 1 subshell. At subshell 2, we have S's and P's. At subshell 4, we have S, Ds, and Ps. At subshell 6, we have S, D, Fs, and Ps. So the higher the shell, the more subshells we have within it. And the reason for that is we have more electrons to account for. So we keep subdividing those into these stability areas called orbitals. And that's what makes up the whole organization of all the electrons. So the simpler the shell, the lower number of the shell, the simpler the subshell organization is. So in the case of shell number 1, we just have S's. Okay, so helium, that means it is 1, because we're in shell number 1, only S's. And how many S's do we have? We have 2. Okay. So the first number is the shell. Second one is the subshell. And the superscript is the number of electrons in the subshell. So we have to account for every single electron when we do electron configurations. Okay, I'll repeat that. We have to account for every single electron when we do electron configurations. We have to account for where they are, what shell level they are, what subshell they are. And on Monday, we're going to talk about what orbital they're in. And these are all neutral atoms so far. On Wednesday, we're going to talk about ions, which means they're going to be either more or less electrons. Okay, so that's helium. Now notice helium is on shell 1, so is hydrogen. And there's no core electrons below that. In other words, if you're on shell 5, you've got shell 4, 3, 2, and 1 that are below you. Okay, and those are the core electrons. With helium, there's nothing below the 1. So that means there are no core electrons. Okay, so let's look at lithium. Okay, now lithium is here. And notice lithium is on shell 2. That means it has a shell below it, shell 1. So lithium has both shell 1 electrons and shell 2 electrons. So we're going to have to account for both shell 1 and shell 2 electrons for lithium. Lithium has 3 electrons because its atomic number is 3. That means it has 3 protons. This is a neutral lithium, so that means we have equal number of electrons and protons. Okay, and so lithium is sitting right here. Notice it has shell 2 has the potential to have S and P electrons if we have enough electrons. Okay, so 3 electrons. We have 1, 2, 3 electrons. We don't get to P electrons. We only have 3 electrons, so we only do S electrons. Okay, and I want you to follow that. How do we get to lithium? Well, we look at starting up here at shell 1 and go, well, we have S electrons, S electrons, S electrons. We never get to the P's because we don't have enough electrons to get there. Lithium only has 3 electrons. Okay, so let's look at lithium now. So lithium has shell 1, it has s electrons, and there are 2 of them. And because lithium is in shell 2, we have to account for that 1 electron that's in shell 2. And that 1 electron is an s electron. Okay. Now, because it's in shell 2, that means it has core electrons. Okay, so we're looking at the highest shell number. That's the valence shell. It's the highest number. The valence shell, if there is a shell below it, that is the core shell. And that core shell is below the valence shell. So if you're at 5, then you've got 4, 3, 2, 1 below you, and those are all cores. Now there's a little bit of complexity I'm going to talk about, but in general, whatever you are, if you have something below you, those are cores. Okay. All right. So
Can I please ask a question?
absolutely, go ahead.
Could you please clarify the difference between orbital and shells?
Don't worry about orbital right now. Okay. There,
Okay.
I want you to clarify the difference between shell and subshell
All right.
as opposed to orbital, because orbitals are within the subshell, and I'm going to talk a lot about that on Monday.
Okay.
Because subshells are composed of orbitals.
On the example that you did,
Yeah.
I believe it was on Tuesday, you did this for magnesium, I think, but I can't be sure. And it also had the P subshells.
Yes.
Yes, and
I'll do magnesium in 12 seconds. How's that?
all right, thank you.
Okay. All right. And thanks for kept bringing me back. Okay. Remember, everyone, that's the advantage of sitting in on these lectures. You get to ask questions. And then the cool thing is everyone else has got the same question. They're going like, oh yeah, that's a good point. Okay, so keep me honest, you guys. All right, so reviewing lithium now. Lithium's got 3 electrons total, and we know that because its atomic number is 3. Means it has 3 protons, 3 electrons, assuming it's neutral. Excuse me. And we can account for all 3 electrons with the electronic configuration. Now, that means that plus that. So we have now accounted for all 3 electrons. 2 are in the core at the 1 shell level, and 1 is at the 2 level, the valence shell. Between the core and the valence, which do you think is more stable?
The core.
Core.
Exactly. That's because it's closer to the nucleus. Electrons are negative, nucleus is positive. So when you get closer to the core, those are attracting. So that's a more stable place for electrons. So exactly. So the core is more stable than valence, and core is horrendously stable. So they never do anything because they're already stable. Valence electrons, however, are not stable unless there's a particular configuration where they are stable, but in general, they are not stable. And that's where all the chemistry of that element comes into play, is in the valence electrons that are located in the valence shell. Okay, so let's come up with another example. Oh, magnesium would be good. Okay, so let's look at magnesium. And where is magnesium located? Magnesium is located here, right? So it is in the third shell. So that means there are two shells below that. Those two shells below that are core electrons. The 3 level are the valence electrons. Okay. And how many electrons does magnesium have? Magnesium has 12 electrons. So we have to account for all 12 of those electrons. Okay. So let's look at this here now. Okay, so how do we get to magnesium? Well, we've got shell 1 electrons, shell 2 electrons, shell 3 electrons. So if we kind of go along this path to get to magnesium, we are going to go through all the levels of shells and subshells to get to magnesium. To do that, we have to go through 1s, then we go through 2s and 2p, and then we finally get to magnesium at 2s. Okay. Electrons. Okay, so when we're going through the first level shell, that's 1s2. 1s2, 2 electrons. Then we went to shell 2, 2 electrons, 6 electrons. Two electrons, 6 electrons. Okay. Now, how did I come up with 6? 1, 2, 3, 4, 5, 6. 1, 2. Okay. Now we're not at the 3 level yet. Okay, we're only accounted for 2, 2, 6. That's 10 electrons. So we have 2 left. So that's where magnesium is right here. 1, 2. So let's look at this. What do we have here? That would be the valence shell because it's the highest. And that means these guys are core. And which, between the two of them, which do you think are more important?
Valence.
Yep, exactly. The valence are more important because those are the most unstable. And they are going to influence the chemistry of that element. The core electrons, again, are super stable. Super stable means they are not going to go anywhere. They are happy to be exactly where they are. They're happy to be core electrons. Valence shell electrons are not happy because they're unstable. And what happens is they want to become more stable. When they become more stable, that's when they want to move to. Okay. So that's why most of the elements of the periodic table, except for the noble gases, are unstable. So what happens is that they want to form compounds. And when they form compounds, they're more stable because their valence shell electrons are combining with other valence shell electrons. And that combination makes them more stable. And we're going to talk a lot about that stuff in here, okay? As we progress through the semester. Valence shell electrons, what are they doing? How are they combining? Are they transferring? Or are they sharing? Or what are they doing? Okay, so the configuration for magnesium would be 1s2, 2s2, 2p6, 3s2. That's the electronic configuration for magnesium, which contains core and valence. Okay, you guys okay with that? All right, let's try, let's do phosphorus. Okay, phosphorus. Where is phosphorus? Phosphorus is right underneath nitrogen. It's also a shell 3 element. So that means it has two shells below it, shell 1 and shell 2, which of course are core electrons. And notice that magnesium has 2 below it also, shell 1 and shell 2. And those are going to be the same. The same. Okay. All right, so let's look at phosphorus now. Phosphorus is going to have 15 electrons we have to account for. 15 right here. Electrons. Okay. All right, so 15 electrons. Well, we already mentioned it's in shell 3. Excuse me. Okay, magnesium was in shell 3. So it's going to have the same shell 1 and shell 2 electron configurations. So we can just write that out. 1s2, 2s2, 6. And now what about, now those are the core again. Let's do that in yellow. Now we need to deal with the valence electrons. That's shell 3, okay? So if we look over here, that's where phosphorus is, which is right here, third one over. Okay. Third one over. So we have 2 over, that's with the S, and 3 over into the P's. So the configuration should read, superscripts tell us how many electrons. So we have 2, 4, 6 is 10, 2 is 12, plus 3 is 15. So we have to account for all the electrons. Now, oops. These are valence electrons, core electrons. Those don't amount to anything because, again, they're super, super stable. The valence electrons are going to make the chemistry for phosphorus. Now, let's look at, any questions so far? Let's look at nitrogen now. Nitrogen is located right here. Nitrogen is in the P subshell. So that means we're going to have some P electrons for nitrogen. And how many total electrons are there? There are 7. 7 for nitrogen. Okay. All right, so let's go down to nitrogen now. Okay, so nitrogen is going to have Okay, so nitrogen is in shell 2. That means it has a shell below it, shell 1. Shell 1, because it's below shell 2, are the core electrons. Shell 2 are the valence electrons, and it has S's. Let's clean this up here. And this is where nitrogen is located. That's where nitrogen is located. And so it's got, this would be shell 1, shell 2. Nitrogen is in shell 2. That means the core electrons are in shell 1. That's a 1s, 2. Okay. To get over to nitrogen, we need to have 2 s's, 3 p's. Okay, so this is core. Okay, so valence are 2 shell. That's the highest shell number. Okay, and notice there are, oops, 2 core electrons, 5 valence electrons. So a total of 7 electrons. How many electrons are in nitrogen? 7. So we accounted for all the electrons. So whenever we're writing these electronic configurations, we have to account for all the electrons. Excuse me. Now, are we okay so far on phosphorus versus nitrogen?
Yes, I have a quick question about the table for the S's and the P's.
Say again on the last part. Speak up too.
I'm sorry, I'm on my headset. Are you able to hear me now?
Yeah.
For if you go up a little bit, if you could go up just a little bit. Yes, for that table for the shells and the outer shells.
On the left?
Yes. Can we get a paper like that, or is there like a little note figuration we could do with this? Like print it out like this?
I can make one.
Okay.
Could you do me a favor and send me an email to remind me?
Oh yes, of course.
Yeah, and I'll do that in.
Okay, thank you.
Yeah, that shouldn't be too hard. Okay. Is that your only question?
No, I have a question regarding this last example we just did.
The nitrogen or the phosphorus?
Nitrogen.
Okay.
So you said that the initial S was core and then the S and P were valence. So did you say that they were valence because they were in the same shell?
Yes, and they're the highest shell. Okay.
Okay, so even if the S and P and like any subshell, even if they differ, as long as they're in the same shell, they're still valence electrons.
Yeah.
All right, thank you.
Exactly. Perfect. Okay. And the two down here. Oops. I was on my erase. Okay. All right. So these guys, because it's one shell down, automatically makes them core. It doesn't matter if it's 4 or 5 down, but it's down from the highest shell. Automatically makes it core. Okay,
Sounds good. Thank you.
you're welcome. Okay, now remember when we talked about the periodic table, and I said groups in the periodic table, and I mentioned this on Tuesday, but the periodic table is organized two-dimensionally so that the vertical columns have chemistry that is extremely similar. Chemical characteristics, the chemical reactions, et cetera, are similar. Why is that? Okay, now we know why. Now we know why. Why? Because the valence configurations are the same. Okay, now let's look at phosphorus and nitrogen. How many S's does phosphorus have? 2 S's. How many P's? 3 P's. On nitrogen, how many S's? 2 S's. How many P's? 3 P's. Gee, notice they're the same. Therefore, chemistry is the same. Because I keep stressing the valence electrons determine the chemistry. So if the valence electron structures are the same, then the chemistry is the same. Okay, so now you know technically why phosphorus and nitrogen act similarly. And that is why in your bodies, you'll find a lot of nitrogen and phosphorus compounds. Something called phospholipids, nitrogens are in heterocyclic compounds all over the place. Phosphorus compounds are all over the place in your body, and they're used interchangeably because the chemistry is the same, because their valence configuration of their valence electrons is the same. Now, what's different between the two? Well, phosphorus has more electrons. That means it has more core electrons. Number two, let me write these down. Okay. So what's the same between nitrogen and phosphorus? Okay. Valence electrons are, let's see, have the same valence configuration and number. Therefore, okay, you need to get used to these 3 dots. Okay? In analytical sciences and math and engineering, 3 dots mean therefore. Therefore, chemistry is the same. But they're not the same atom. So what is different then? Okay. Different number of electrons. More core electrons. More protons and neutrons, hence the atomic mass is different. But because the valence electrons are the same, the chemistry is the same. Okay, so they are not the same atom, but their valence electrons are configured the same, hence their chemistry is the same. Now you can say that for all the groups. That means lithium's valence electrons are the same as sodium's, potassium's, etc. Beryllium, magnesium, calcium, strontium. Now let me tell you a problem with that in our environment. Whenever we have a nuclear accident, frequently, if not all the time, a radioactive strontium is produced. 3 Mile Island, Chernobyl, Fukushima, Hiroshima, Nagasaki. Anytime there's a fission reaction, splitting of the atom, we have usually strontium produced, and the isotope is very radioactive, very, very deadly. Why is that a problem? Can you guys think of an issue with that being a problem?
The isotope of strontium being radioactive, is that the question?
Yes. Why is that a big deal?
Because it's not stable.
True, it's not stable, but they produce a lot of isotopes. But why particularly, excuse me, why particularly strontium is an issue?
Will it create a chemical reaction?
Yes, that's true. Now I want you to think about your bodies. Think about the periodic table. And we were just talking about, remember, valence, chemistry, and all that stuff. And think about your bodies. Think about why that strontium would be bad for you to be around.
Because of the radioactive.
That's true. It is radioactive, but why is it particularly bad?
I'm assuming it would cause burning sensation in the lungs, maybe?
Definitely that. Okay, everyone.
It can also cause cancer.
I'm sorry, what?
Can it not cause cancer?
It does, causes leukemia. Why do you think so?
Because it reacts with your body's chemicals?
Yes, which one in particular?
Your blood?
And where's your blood made? That's right. Where is it made though?
Oh, the bone marrow, right?
Yes. Yes. And why does your mother always want you to drink milk?
To keep your bone marrow strong.
Calcium.
For calcium.
Calcium. And what is the valence configuration for strontium and the valence configuration for calcium look like?
5s2.
And that's right. And calcium is?
4s2.
Yeah. And is that valence different or similar?
Similar.
Yeah. So that means your body is going to take in strontium instead of?
Calcium.
Exactly why? Why would your body do that?
Can't tell the difference.
Yeah, because the valence electrons in strontium, the 5s2 are the same as the 4s2. That means your body thinks it's pulling in calcium, but it's pulling in strontium, and this particular strontium is very
Radioactive.
exactly.
Not good for you.
Exactly, and guess where it goes?
In your blood, and you got a lot of blood in you.
Into your bone marrow, which makes blood cells, right? And that's called leukemia if you can't make enough red blood cells. So when you're around, that's why you wear badges, dosiometer badges on whenever you're around, like you're a X-ray tech or something like that, or you're on a submarine, you're a tech working the reactors or whatever. You always wear a dosiometer on your clothing, because they don't want that strontium to go above a certain level, because your body will take it in thinking it's calcium, because the valence electron configuration is the same. Bad stuff, strontium. Guess what happens when you have a nuclear bomb? You have something called radioactive fallout. What's that?
When it causes death to like living things.
Yeah, exactly. Well, but what is fallout? You're absolutely right. But what is it?
Like an explosion, like where everything just explodes into the air.
Yeah, and what's in the air? When you see that mushroom cloud in the air, what is it?
Dust.
Dust, exactly. And it's radioactive dust. It goes up to about 60 to 80,000, 90,000 feet in the air. And guess what? It's spread all over the place. And then it comes down on fields. And where do dairy cows pasture?
Fields.
Fields. So they will, if they're around a nuclear fallout area, they will ingest radioactive strontium, because it's falling as dust onto the grass, into the pastures. They will eat it, it'll go into their bone marrow, and their milk then is becoming bad because it has radioactive strontium in it. So
What
this
about
whole,
the soil? I'm sorry, is the soil also affected, like for growing crops later?
yes, yeah, it's really awful. It's really awful. And let me give another little tidbit. And whenever military fires bullets at one another, big bullets are armor piercing. They go through metal, they go through tank walls, they go through all stuff. And guess what? They're made out of depleted uranium. And military can shoot hundreds of thousands of these rounds. And if you're in the same area, like in Afghanistan, those shells are being used all the time. So these areas where there's military conflict, things like depleted uranium shells are all over the place. And our world is becoming, it's like, we're doing all this stuff to our environment. That's crazy. It's crazy. But anyway, the example I wanted to use is strontium. Now, another thing. Okay, I go to the doctor. Doctor says, Ferguson, your blood pressure is high. You need to get off sodium diet. You guys, what do you think I should do? But I like salt, by the way. Okay, in sodium chloride salt, table salt, the chloride part of the sodium chloride is what's salty tasting. So what do you recommend I do? Because I like salt, I like to cook, and bland things I don't like. I like, my salt. So what do you recommend I do to lower my blood pressure?
Replace the sodium part with another chemical, I guess.
Exactly. And what chemical would you suggest?
Magnesium?
What's in the same group as sodium?
Potassium.
Potassium and lithium. Okay, lithium is very bad for you. But potassium is called, who knows what potassium chloride is called? Light salt. So we get the chloride part, the salty part, but we don't get the sodium part. We get the potassium instead. And why do they act the same? It's because potassium and sodium are in the same group. Hence, its valence chemistry is the same. So this concept of valence electron configuration is a big deal. Big deal. Why do you think they use silicone when they're rebuilding body parts?
Because their bodies are made of carbon and they're in the same column,
Yeah.
same
exactly.
valence electron.
Yeah, exactly. You got it. Sulfur is used a lot in our body, and so is oxygen. They're used interchangeably. So you'll see a lot of sulfur. You'll see antibiotics, for example, penicillin antibiotics have sulfur in them and stuff. And our body thinks it's oxygen. Anyway, so this whole idea of column valence chemistry is real important in nature. When you look at this column here, we have copper, silver, gold. I mean, silver and gold. What are the characteristics of silver and gold? They're anti-corrosion. You don't find them a lot in nature. They have real high conductivity. Copper, high conductivity. They use it in wire. There's a reason. They use gold in microelectronics because of the corrosion resistance. Why do all three of those have similar chemical characteristics? They're in the same group. Hence, their valence configuration of their electrons are the same. So isn't that cool? Now you know technically why the group's chemistry is almost the same. Not exactly the same, but very, very close.
Isn't it that as you go down a column, the properties are more enhanced, if that makes sense? So is that why gold does a better job than copper? Does that make sense?
Yes. Yes, it makes a lot of sense. One of the complexities, though, is you go down the column, you get more and more electrons. And those electrons, for example, gold electrons, there are some electrons that notice down here. Gold has got an atomic number of 79. Notice this stuff down here has got numbers less than 79. That means you're incorporating F electrons into gold, where silver has no Fs. So there's some, as you go down, the complexity builds up. So things change a little bit. Copper and silver are more closely related than gold and silver, because there's no F electrons involved with copper or silver. And I'm going to go over that again on Monday. We'll get into some of these much more complex ones. But today I want you to understand the simple ones. Basically, those are the fundamental ones. Okay, shell 3 downward. We get into shell 4, we get involved with D electrons. We get on shell 6, we get involved with F electrons. And the weirdness is the subshell numbers change a little bit. But I have some little things to help you memorize that. Okay, so today though, I wanted you to feel comfortable being able to configure some of these compounds there. Okay, so I'm going to end it, but I'm going to do one more. And let's do chlorine. Okay, and chlorine, it's got 17 electrons and it's in shell 3. Okay, so how many total electrons does it have? It has 17. So we need to account for all 17 electrons. And it's in shell 3. Excuse me. So it's got shell 1 and shell 2. Shell 1 is 1s2. Shell 2 is 2s2, 2p6. And because we're in shell 3, that means those are core. And because that's where chlorine's located. So it's in the 3p subshell. So it also has 3s electrons. Gotta write this big, huh? Let's make this smaller. No, chlorine is located 5 spaces over. So that means we have 1, 2, 3, 4, 5 p electrons. Okay, so do we have our 17 electrons? Well, let's look. We have 2, 4, 6 is 10, 12, and 5 is 17. So we've accounted for all the electrons. Now, if we look at fluorine, above chlorine, it's got 1s2, 2s2, 2p5. Core, because it's less than the shell, the valence shell, so that would be core. And so we have okay, this would be valence. And again, look at the valence configuration. S2, P5, S2, P5. Hence, chlorine and fluorine are members of the halogen group. Hence, their chemistry is the same. Okay, so I'm going to end this now. I'm going to pick up on Monday for looking at some of the stuff in this area. But it's important you understand this area though. So you should be able to write out the configurations for everything up to argon, which is right here. So argon is be 3s2, 3p6. And send me that email about doing this for you. I will do that. That's a good idea. Okay. So, any questions, you guys?
I have a question. Sorry, go ahead.
Oh, no, you go ahead, dear.
Thank you. I have a question about the worksheet answers for chapter 3 and 4. I was trying to work on them, but the answer key only contains the odd questions answers for some reason. Have you seen it?
Yes. The reason for that is the department, some professors use the even number worksheet problems for test questions. So I can't give you the answers for the even ones. Because if you have a friend in another 300 class and you can supply them with the even number of questions, those may be on a test. That's why it's odd. Normally, I give you all the answers because my questions on the test never are directly a copy. They're totally different. But other professors don't do that. So I can only give you the odd answers. Does that make sense?
It makes sense. So when we're practicing for the upcoming exam, is it still okay to ask some of the questions that we couldn't solve that were actually even numbered?
Yes. But I'll probably give you a parallel example.
Okay, thank you.
Essentially, I will answer your question. No
I
problem.
have one last question. I know you went over this, but just to reiterate for the quiz that's due this Sunday evening, it covers chapters 3 and 4, but not 9.
Correct.
Okay, thank you.
And it's multiple choice and true false. So it'll be graded within, after you click save, it'll be graded within 2 seconds. Because I've already put all the answers in and all that stuff.